Okay, so now we're going to get into a discussion of thermochemistry. Thermochemistry, as the name suggests, is that area of chemistry which looks at energy changes in chemical reactions. And that will be the focus of this chapter. But before we get into the actual relationship between energy changes and chemical reactions, we have to define some terms firstly. So the first one I'm going to talk about is energy. What is energy? Energy is the capacity to do work. So basically, energy is said to be done when force is applied to an object and the object moves. All right. Now, the literal meaning of the word energy means work within. However, objects do not contain work. They basically contain energy of one form or another. And therefore, there's some confusion sometimes when people use the terms energy and work as if they mean the same thing. Now, under the broad category or the broad universal concept of energy, there are two subcategories. You have what is known as potential energy, which is the energy an object has by virtue of its position or composition, and you have kinetic energy, which is the energy an object has by virtue of its motion. All right. And in terms of the kinetic energy, we can calculate it for any object using this equation. EK, which is the kinetic energy, is equal to half mv squared. Now, you have to be careful about the units in this particular equation because you'll notice that the energy has units of joules. And it turns out that joules is the same thing as kilograms meters squared per second squared. So what that means is that in this equation, if the mass is in kilograms and the velocity is in meters per second, then the units of energy, in this case kinetic energy, will be joules. All right. So that's one important thing that you have to keep in mind when using this particular equation. Okay, as I said before, thermochemistry is involved with the relationship between chemical reactions and the energy changes that occur. But there are some other terms that you need to be familiar with because we'll be using these terms right throughout this chapter. So whenever we talk about a system or a system, we are talking about the part of the universe that is being studied. And that could literally mean any part of the universe, right? So in the context of chemistry, that could mean, for example, a reaction occurring in a vessel like a test tube or a beaker, all right, or a flask. And then the surroundings would, of course, be the rest of the universe. So when it comes to systems, there are three types of systems. You have the open system, closed system, and isolated system. Now, in the case of an open system, you can have the free exchange of energy and matter between the system and the surroundings, all right? So, you can have, any chemical going in, chemical going out, and the same is true for heat as well, or energy in general as well. A closed system is one where you can have exchange of energy between the system and surroundings, but no exchange of matter between the system and surroundings, all right? And then finally, we have what is known as the isolated system. And in that particular case, there is simply no exchange of energy or matter between that system and the surroundings. So these are some other terms that you have to be familiar with because, again, we'll be using these terms a whole lot in this particular chapter. So let's talk about the various forms of energy. As I said before, energy can be put into two broad categories, potential and kinetic, but within those categories you have subcategories and you have some overlapping situations where forms of energy can exist in potential and kinetic forms. So let's talk about this term, internal energy. This is a total energy within a system, and it can be, of course, part kinetic and part potential. Now, the kinetic part has to do with the movement of particles, right? Any object that is moving, as we said before, has kinetic energy. So if you think about particles like atoms, molecules, and so on, as you can imagine, there are different types of motions that are associated with these particles. You have translational motion, you have rotational motion, where you have a molecule rotating around a particular axis, and then you have vibrational motion. Now, in the case of vibrational motion, you can have, for example, in a bond where you have two atoms connected, the bond kind of act like a spring, and therefore you have the vibration, just like if you have two metal objects connected by a spring and it's vibrating in and out. Well, basically, it's the same idea when it comes to vibrational motion. And collectively, these are sometimes called thermal energy. And the reason why, as we're going to see later, is that these forms of energy, or I should say internal energy, is actually related to the temperature, right? We're going to see later on that there's a direct linear relationship between the temperature expressed in Kelvin and the internal kinetic energy. Okay, and then the other part of potential of internal energy would be potential energy, and these would be basically the type of intermolecular forces and intramolecular forces of attraction between bonds, between atoms as a result of bonds and so on. And collectively, these energies are known as chemical energy. So the type of forces we're talking about here is the electrostatic forces that exist, for example, between the nuclei of atoms and the shared electrons in a covalent bond, all right? And there are other types of forces that exist between molecules, which we'll get to later on, not in this chapter, but for example, you have van der Waals forces, hydrogen bonds, and so on. And the energy that hold these, that is responsible for these forces, are different forms of potential energy. Okay, let's talk about heat. Heat technically is not energy per se, even though in everyday language, we tend to use heat and energy as if, well, basically saying that heat is a form of energy. But the actual definition of heat is that it's an energy transfer that occurs between a system and surroundings, which is caused by a difference in temperature, right? And basically to illustrate what we're talking about here, for example, let's say we have this hypothetical situation where we have argon molecules, or argon atoms, I should say, on one side of a hypothetical thin wall, and nitrogen molecules on the other side, which would represent the surroundings. So basically what will happen is that these gas particles, these atoms and molecules are always moving. We know about that from the previous chapter when we talked about the kinetic molecular theory. So of course there's a temperature energy relationship. So basically what happens when you have heat transfer is that the faster moving or the more energetic particles will collide with a hypothetical thin wall and will transfer that energy to the molecules in the surroundings, right? And therefore, as a result, you have the heat transfer. So the energy transfer resulting from what we just described here, that is what we call the heat transfer. And therefore, the heat will be transferred from the more energetic molecules to the less energetic molecules. And as a result, that's basically what happens when heat is transferred, all right? And this heat transfer will take place continually until you get to a point of what we call thermal equilibrium, right? And what do we mean by that? That occurs when the system and surroundings reach the same temperature, and at that point, you'll have no more heat transfer. And this is also a very important concept that will actually become useful when it comes to solving certain problems, the whole concept of thermal equilibrium. Basically, at that point, the temperatures of both the surroundings and the system will be the same, all right? Now, before we move from this particular slide, I want us to look at this question. It says, how do the root mean squared speed of the argon atoms and the nitrogen molecules compare at the point of thermal equilibrium? All right, so let's look at that question. Let me bring up this right here. And let me choose, well, let me do this first. Let me choose a pen, ink. Okay, so we're talking about comparing argon. Okay, why is this thing not writing? So let's compare argon to nitrogen, right, which exists, of course, as N2, all right? Now, the molar mass of argon is, let me look it up. The molar mass of argon is 39.95 39.95 Okay, this thing is not working out. Okay, you know what? Let me just stop this video here, work out this situation, and then get back to you with this problem. So let me